Lesson 76, motion and energy. We will discuss how motion and energy affect each other. So ultimately, when we talk about motion, we can talk about it in terms of energy, as I just sort of said. And energy is going to be this main key point. It's going to keep coming up over and over and over again, no matter what topic you choose in physics, because ultimately you can almost think about physics as an understanding of energy. Now, this is sort of backing off what we've been doing the past two lessons, but it's a bit of an extension. Let's talk about what we did last two lessons. The last two lessons we looked at work, which is a force over a distance or a force over displacement. You calculate work by what is it being forced against. And then what we did was we looked at, well, how can you use work to understand things? You can use work to sort of explore mechanical advantage. Then we talked about force distance graphs. And these force distance graphs are used to sort of understand what happens when you apply a force to something, and you measure how that force changes over distance. Does that force go down over distance? Does it go up over distance? And you can use that to calculate the energy, which is the area under the graph. And then I gave you guys some time to work on 11.2 and 11.3, and that was yesterday's goal. Now, today's goal is to talk about not just work, because work is a part of energy. Work is when you act against the force. You have to apply a force to something to do work. What we're going to talk about is energy. Well, when you apply that work, what happens to it? Essentially, that's what I want to know. Now, the first thing I'm going to say is this. When I made these slides at 1:30 in the morning. They are not necessarily very pretty, and there are a lot of empty spots in these slides. And the reason that I was doing it so late was because I had to do all those that reporting that I just showed you in the previous slide. So unfortunately, don't necessarily look at these and go, oh my God, and there's going to be a fair bit of me writing on slides instead of normally what would happen is there would just be already written slides and you guys would just, copy down what you need to. And the reason for that is that I thought, well, because it was very late, I thought what I'm just going to do is I'm going to put a couple of slides up there and then I'm going to talk about them and use my pen, because I have that up now, just to write down things in the slide that I think are important. So let's make a start. To talk about energy, we need to talk about two major types of energy. We need to talk about how they're important and then how they calculate them. By the way, keep your eyes peeled, because for this lesson, normally I introduce one new formula. For this lesson, there are 4 equations that will pop up. And these 4 equations are going to be equations that you guys are going to be expected to be able to do. So keep your eyes open for those. You may want to highlight them when they do show up. So the first rule of energy. And this is where I think is a really good place to start. Whenever we talk about energy, it's always a good place to start with this. The rule 1 of energy is always conserved. And this is something that I remember teaching students way back in year 8. Energy is always conserved. It may change form, but it must be accounted for before and after any interaction. So when light falls on a leaf, that light is the form of energy. That light has to get absorbed by that leaf, and that might be absorbed and transferred into chemical energy. That light is also going to be a form of energy that hits the ground. So the ground is going to absorb that energy. What happens when light hits the ground is it heats that piece of ground up. It leads to a change in temperature, because remember, light is just going to be Q. It's just heat coming in. That energy has to be accounted for. If you eat that plant, then that plant is going to turn that chemical energy into more chemical energy for you. And you might turn that chemical energy into some kind of motion. You could instead burn that plant and get heat out and thermal energy. So there's all types of energy. So whenever we get an energy transfer, we have to remember that energy is conserved. So that's our first number 1 rule. And I always like to just start with that, because that's going to be our basis for everything. Let's now talk about, well, okay, if energy needs to be conserved, well, how can we understand energy? What can we do to better grip you get a better grips of understanding of energy. We've already got our formulas from way back at the start with regards to thermal energy. What about just energy in general? So to do that, we're going to look at this. Gravitational potential energy. Now, I'm actually going to start with this. The book does this in a different order. Most books do. I'm actually going to start this in a weird way because I want to try and, in my opinion, I think the best way to teach this topic is just to sort of like to start off with stuff that we already know first. So if you guys remember yesterday, I asked an attendance question where I said, if you take a bag of rice, you move that bag of rice up onto a shelf, how much work is done? And the best way to calculate that is to use the mass of the rice, and we have to know, and we can use the gravitational acceleration, because that's what it's doing. The rice is getting pulled down by gravity. We're pulling it up against that gravitational force. And we also need to know, to work out how much work we've done, we need to know how high this shelf is. How much are we, what distance are we applying this, what distance are we applying this force over? That's what I want to know. So we can think about this as, we can think about this again. We're going to stick to just looking at work. By moving the rice up onto the ledge, I did work against gravity, okay? I did work against the gravitational force. And that's actually when we use the word work, you're always moving it usually with a force. So you're usually moving it against the force, moving it against the force of gravity, moving against the force of friction, moving against the force of, I don't know, magnetism. So in this case, I did work against gravity. But here's the question, and they go, so work equals force times the displacement S. Now we know that the force is mg because force is equal to mass times gravity. And we know that so the work done on this bag of rice is the mass times gravity, because this is the force, multiplied by h, because that's our displacement. That's how high we're moving it up. So it's just a different way to sort of explore that idea of work. We're putting energy in, which is equal to the mass times the gravity times the height. Now, okay, so how do I then build upon this? So here's the question, but the energy must go somewhere, okay? We can't just do work, and work is a form of energy. We're putting effort in, but where is that energy going? Like, you can't just, do work and move that bag of rice without that energy going somewhere. And in this case, it goes into the rice. Now, it doesn't go into the rice in that it makes the rice warmer, like you would say if you were, it doesn't go into the bag of rice if you're squishing a balloon that might hit the balloon up. No, in this case, we're putting the energy into the rice, but we say in this case, it's not in the form that we would usually refer to it. It is in the form of gravitational potential energy. Okay, that means that we've stored this energy. We've stored this mgh energy in the form of this potential energy. And the formula for that, and this is our very first formula that we're going to have to memorize, equals Eg equals mgh. The gravitational potential energy is equal to the mass times the gravity times the height. It's the same formula as this. The only difference is I've replaced W, which is the work done, which is how much work I put into moving that rice, into Eg being a potential energy. Now, the first question that then becomes, that we then show up is, okay, so what the whole point of this slide is to say is that by doing work on an object, you are storing energy, okay? So you are creating potential energy, the potential for something to happen. So we refer to that energy, and how we can calculate it is we say, well, we have to do a force against gravity. So it's mg, and height is how much we're going against gravity. Now this is fine, this is actually really good, but what we're missing out on here is we're missing out on understanding of what this word means. And that's what we're going to move on to now, potential energy. What is potential energy? Now there's no words on this slide, so I'm going to be doing this. Potential energy is what we refer to as stored energy. Potential means it can do work. It can do work. So potential energy means it can, doesn't have to, but it can do work. Or you could think about it, or it can release energy. It can release energy. Potential energy is measured in, of course, joules, just like its normal regime. It can do work or it can release energy. That's the main idea with potential energy. The energy, I'm going to write this energy is stored by doing work against a force. And that's exactly what we just saw. We can store energy by moving an object from the ground up onto a table. You are giving it potential energy. If you were to take a spring and you were to compress that spring, that is storing potential energy. If you were to take a magnet and then you were to remove a nail from the magnet, that would be creating potential energy, because you are doing force against the magnetic field. That nail wants to move towards that magnet, but you are not letting it. So it's got the potential to move, but you are not letting it do that. And that's what we talk when we refer to potential energy. That's what it is. When you move the object when you move the rice up onto the top shelf, that rice could fall down to the ground and release its energy, but it won't, because it's on a shelf. Okay, it's on a wooden shelf. So we say, well, because it could fall down, it has potential energy. So potential energy is the ability for something to do work on a system. It's the potential for something to release energy. And that if it fell down, it could release that energy and smack into something. It could release that energy as a force acting to smash something. If you were having a magnet, it can release that energy in the form of motion, in the movement of the nail, so on and so forth. So then we talk about potential energy. Now, of course, the classic example of potential energy is what I've got right here. I've got a battery. Now, a battery is essentially potential energy locked up. In this case, it's we have an understanding that the reason that there's potential energy here is because there is a lot of electrons here that want to get to this positive side of the battery. How did we create this potential energy? Well, what we did is we created an imbalance of electrons. And how did we create that imbalance? We used chemistry. But this is chemical potential energy. And when you can actually refer to potential energy in chemicals as well. You can be like, well, these two chemicals, when they react, they could release this energy. So you refer to this as potential energy. Something like an explosive has a high potential energy because it's got a lot of energy that can be released. Other things might have lower potential energy, whereas when they react, they won't necessarily react and release as much energy. In this case, there is locked chemical potential energy in a battery. And so when that battery gets attached to a certain way, it can release that potential energy in the form of moving charge. And that's how we get current and voltage. So that's when we talk about a battery, that's a different way to think about potential energy. So potential energy is stored energy, but there's a little bit of an issue here, right? I'm going to show you this. If I took these two mugs, right, if I took these two mugs, right, and I dropped them, right, let's say they're the same height, right? Let's call this height 1.2 meters, right? And so this one is 1.2 meters. Now here's the thing, right? Both of these are the same distance off the ground. So if you calculated their height, mgh, you could get the same value for the mass. But here's our issue here. If I drop this one on the left, it will fall down and it will hit the table. And it probably won't shatter. But if I drop this one down and hits the ground, guess what? It's probably going to break up into, 10, 12 pieces of mud. And here's the question though. But the question you might say is like, but they both have the same gravitational energy, don't they? And here's where you have an issue. Yes, they have the both same gravitational energy if you do the reference to the ground. Here's the thing. When calculating potential energy, it is important to have a reference level, or E0, at a point where there is zero energy. So even though, yes, they both have the same gravitational energy compared to the ground, this on the left has a different potential energy if you instead calculate this. Let's say that's 0.2 meters. That's going to give it a different value of energy. So if I drop it and it only falls 20 centimeters, it may not shatter because ultimately the energy stored up in it is less. We refer to this as a reference level. A reference level is the point that we take to have zero energy. So we sort of both agree that we sort of agree for both of these, when it reaches the ground, it has zero energy. But for the one that's above the table, that's going to have a different amount of energy. And the reason it's going to have a different amount of energy is because we're going to refer to it in reference to the table. Let's do some basic calculations here just to really cement this idea. Let's say the mass of the mug, let's say its mass is, it's 300 grams, okay? And so we say gravity equals 9.8. So if we calculate the energy, E equals mgh of this, it's going to be 0.3 times 1.2 times 9.8. 0.3 times 1.2 times 9.8 gives us 3.5 joules. So whereas this one, because it only has to be called 0.2, let's calculate this one. Eg equals 0.3 times 0.2 times 9.8. It's going to be 0. We're going to round that up. I'm going to call that, equals mgh equals 0.3 times 9.8 times the height, which is 0.2, which is going to come out to be, we're going to round that to 0.6 joules. So if you look at that, with 0.6 joules versus 3.5, after that mug falls, and let's just say that mug hits the table, right? That doesn't mean that mug has zero potential energy reference to the table, but it still has potential energy. It still has about 2.9 joules worth of energy if you take the reference point as the ground. And you might, and the reason for this, and you might honestly be always thinking about this, is like saying, well, what if I dug a hole underneath it? What if the ground was, what if there was a hole in the floor and it could fall down onto the, the level below? If you're in a 2-story building, what if this falls down onto the 1st-story building? Won't it then have more energy? And the answer is yes, it will have more energy. But you've got to factor that into your calculation of where is the gravitational potential energy 0. So it's actually one of these interesting things. And ultimately, this is where it becomes an issue, essentially, with all understanding of energy. There is no such thing as zero. There is no technical such thing as zero energy. Everything has energy. It's just what you're using as your reference. One of the examples is something can always fall. Another example is you could say, well, if you look at this particular mug that's on the table, you might say, well, that mug's not moving. It's like, well, but it's also on the planet Earth, which is rotating very, very quickly. So yeah, it is technically moving. It does have kinetic energy relative to the universe. And so you can always give something energy relative to something else. And that's why I think one of the most important things about energy is relative. You have to measure it. Well, you have to measure it with respect to something else. If you say that a cup on the table has zero joules worth of gravitational energy, that's fine. If you say a cup on the ground has 0 joules of potential energy, that's a different way to interpret it. But doesn't matter which way you do it, you get different answers. I feel like I've waffled a little bit too long here, so I'm going to change the slide now, but hopefully this makes sense. We're going to look at one more idea. We're going to move on to the next idea. So let's look at this falling cup. This cup is being dropped by someone absent-mindedly who's not paying attention. The kinetic energy is a new form of energy, and here we've got a brand new equation. The kinetic energy is the energy stored in movement. So when an object moves, it has kinetic energy. And we use this a lot. We use refer to kinetic energy a lot. And when we talked about the movement of particles, we call it the kinetic energy model, the collision model. So kinetic energy is the movement. The faster or more massive an object is, the greater its kinetic energy. And we've got a formula for this. It's actually equal to a half mv squared. Back when I was giving you guys questions on all the way back at the start when we were looking at thermal motion, there were a couple of questions that said, oh, a particle is moving at 2 meters per second and has a mass of 0.000001 grams. What is its kinetic energy? What is its thermal energy? And blah, blah, blah. And it went on to do stuff like that. I didn't give you those types of questions. I could now, but I'm not going to. So it's got to do with the amount of kinetic energy is equal to the amount of mass times the velocity squared. So something moves faster, it's actually going to increase the energy by a square. So if you double the speed of an object, you're actually going to increase the if you double the speed of an object, you're going to increase the energy by a factor of 4. If you triple the speed of something, that's going to increase it by a factor of 9, so on and so forth. But let's do a basic calculation first before we get into too much of this stuff here. A car has a mass of 1,200 kilograms. It's traveling at 90 kilometers an hour. Calculate the kinetic energy at this speed. Oh man, 90 kilometers an hour. Oh, I didn't read this question before I said it for you. Oh well. 90 divided by 3.6 equals 25 meters per second. If you don't know, if you can't remember whether to divide or multiply, just go back to basic principles. As I said, if you don't remember, just multiply 90 by 1,000 to turn it into meters, and then divide by 60 times 60, and that will get you the same answer. 90 times 1,000 divided by 60 gives me 25. So we've got 25 meters per second. So now let's calculate the kinetic energy. The kinetic energy in this example is equal to half times the mass times the velocity squared equals a half times 1,200 times 25 squared. Can I get you guys to do this in chat, please, for me? Jump onto a calculator just so I can make sure that I get the correct answer. I expect Kelvin will probably be the first person to do it, but like other people, just to confirm that you guys can get the correct answer. So what is that? How much energy is released in joules? That's not what I got, but it's close. Kelvin, be careful. Have a look at your question. What do you guys think? How much energy is there? Can someone say in chat or out loud, by the way? I want some units too. People are looking for their calculators. You know you can use your phones, right?
Wait, so are we doing the like 1/2 times 1225 square, or are we doing the 90 times 1000 divided by 60 times 60?
No, the very bottom.
Or bottom one?
The very, very bottom one. Gives me a break while I'm waiting for you guys to answer this question.
So I missed 10 actually.
You did miss 10, yeah.
Yeah.
I'm waiting for someone else to put in an answer so I can confirm that Kelvin and I have got the correct answer. Anyone will do. 375 kilojoules. Beautiful. Yep, either of those answers will do. I was going to write 300. Oopsies. So I've got 375,000 joules or 375 kilojoules. So that's how many joules there are in the motion of this car. There could be as well, it's stored in other ways, but that's how we refer to kinetic energy in the form of motion. Now, Morris was a bit confused. That's okay, don't stress. Hopefully you guys understand this. You guys can get more of a chance to work on these types of questions a little bit. But now what I want to talk about is I want to talk more about our falling cup. So if you grab a look at it, our falling cup has been falling down, but now it's about to crash into the ground. Okay, let's explore the physics of this for a second. A cup containing some water weighs 300 grams. It is sitting on a 90 centimeter high table. What is its potential energy? Well, let's work this out. Its potential energy, or its gravitational potential energy, is equal to the mass of the cup times gravity times its height. In this case, you know what? No, I want you guys to solve it. Tell me, I want you guys to work out in chat, because you guys are getting a bit lazy in chat. It took so long for you guys to get an answer. I would love you guys to calculate for me the potential energy of the cup. You can message me privately, you can message me publicly, you can say it out loud, I don't care. But I would like you guys to work out potential energy of the mug. Units, Kelvin, units. You will lose so many marks if you don't put units on your answers. It's the right number, but there's no units. Thank you, Fukli. Give me a couple more. I want some more answers. Fukli's giving me one. Kelvin's giving me one without units, but you know that's fine. Can I get a few more answers here, ladies and gents? Show me that you're awake. Show me that, you know, I'm very, very tired here, but I'm trying my best to make sure I'm teaching you guys. So I want you guys to participate as well in the class. Can I get an answer from maybe, I don't know, Andy? I'm sure you're here. Leon, maybe. Tim. Morrison. Yep. Thank you, Morrison. Really good. All right. We'll wait for one more, and then we'll move on. These people, by the way, are messaging me privately. If you're like wondering why there's nothing on the stream, nothing on the chat, it's like, oh, well, you know, one more answer, and then we'll call it that one. Come on, someone. What about, you know, Vince? You've been doing all the homework. Why don't you give me an answer? What about Vu? You're here. Fukli's already given me one. Why am I picking on him? Phoenix, though, you could easily work this out. You've got a calculator. Yep. 200. Okay, you've got the wrong size version, but we'll call it that. Yeah, we'll go with those. The answer here comes out to be 0.3 kilograms, because you can't use 300 grams. You've got to use 0.3 kilograms. Gravitational is 9.8, and the height is 0.9 meters high. Comes out to be 2.646. So we're going to go 2.65 joules. Okay. Now here's the real question. Now, if I drop the mug off the counter, right, all of this potential energy, if the mug is knocked off the table, then how fast will the mug be going when all of its potential energy becomes kinetic energy? Once I knock this mug off the table and it starts moving, that potential energy is going to go away because its height is going to change. It's going to fall towards the ground. And that potential energy is going to be converted into kinetic energy. It's going to be converted into movement energy. We can calculate, and so therefore, we can now say that EG is going to equal EK. When does EG equal EK? When we get to our reference, EG equals 0. When EG equals 0, we know that this is going to be true. All of our potential energy is going to equal our kinetic energy, which is going to be half mv squared. Now, if we know that all of it's going to be converted to 2.65 joules, and we know that equals a half times 0.3 times our velocity squared, we can use this to work out our velocity. Can I get we'll go with 2 answers. I want 2 people to give me separate answers for this. What is our speed? Fukli is straight off the bat. Cool. And, you know, I'll make it 2 answers, but I want someone who hasn't given me an answer before. Maybe Yvonne, haven't given me an answer yet today. And I know, Leon, I know that you are here and you can type. So I want you guys to calculate for me what is going to be the final speed. Someone else, anyone else? Well, someone who hasn't answered yet, you know? I'll read out some more people who haven't answered yet. I haven't heard anything from Anthony. You could do these questions. You could type an answer in chat. Arvin, you could write an answer in chat. Hung, you could write an answer in chat. So could Imran. I want one answer to what is this final velocity going to be. You guys can do this calculation. You can tab out and do it online. Thank you, Kelvin. I appreciate your answer, but I want someone who hasn't given me an answer yet. Kang, what about you? You could do this pretty easily, I'm sure. Ro, no, not quite. Ro, try again. See if you can get your answer a bit closer. Tam, you could do this type of question. You haven't given me an answer yet. As I said, I want someone new, someone to give me who has an answer. Something. Yvonne, thank you, Yvonne. I appreciate it. All right, so we get an answer here. How do we do this? We go the V sorry, give me a sec. V equals 2 times 2.65 divided by 0.3 all square rooted, and it actually comes out to be 4.2 meters per second. Down. Well, it says, no, sorry, it says how fast. So we don't actually need to give the direction. So let's go to 4.2 meters per second. Okay, now, before I move on from this stuff here, this is really interesting. This gives us a new way to do these types of questions. But before I move on, normally I would just be like, yep, cool, we're done here. I actually want to stop for a second and just for one last second, just want to look at something here. I don't like giving you guys new formulas and just being like, yeah, sure. No, there is actually a whole section in the textbook that's just how this formula EK equals mv, the kinetic energy equals half mv squared. There's a whole section in the book about how that formula is derived. Now I thought to myself, should I do that? And I decided no. But what I did decide to do was this. I want to look at this. If we go, and I'm going to look in purple, right? We know that it's falling a height of 0.9 meters, right? We know that its initial velocity when it falls off is going to be 0, but we don't know what the final velocity is. But we do know the acceleration. We do know the acceleration is 9.8. So if we know all of these facts, surely we can calculate the final speed. V squared equals U squared plus 2AS, sorry. V squared equals U squared plus 2AS. V squared is going to equal 0 squared plus, well, in this case, it's going to be plus 2 times minus 9.8 times minus 0.9. So V squared equals 0 is going to cancel out. So we're just going to add minus times minus is going to cancel out. So we're going to have 2 times 9.8 times 0.9, which is going to be 2 times 9.8 times 0.9 is 17.64. So V squared equals 17.64. So V equals the square root of 17.64 equals 4.2 meters per second. Ladies and gents, that's what I wanted to show you guys. These answers are the same. It actually doesn't matter which way you do this question. But what I really want you guys to understand is, yeah, sure, we've got this new formula for kinetic energy and potential energy, but they are based off, at some point, our kinematic formulas. These forms have to be linked. So this is a great way for us to quickly and easily be able to figure out what our final speeds are. But ultimately, and you can even look at this as like in different ways. If you throw an object into the air, if you drop an object downwards, then it's going to have some potential energy because of its height. But you also, if you throw it downwards, you'll have an initial kinetic energy as well. So it's a different sort of way that you can start to really break these formulas down. But I guess what I wanted to show you guys is this formula is not completely new. It's not like reinventing the wheel. It's just a derivation of an old formula. And you guys might see I did not show you guys how you could make this formula, but hopefully you guys should be able to see the similarities here. So if I've got some nerdy students here, I'm talking to you, Kang. I'm sure that you guys could figure out how that formula on the top right becomes this formula mv squared somehow using those like calculations here. I think it's got to do with A times mass will make it a force, and F times S is going to become some kind of work formula, which is energy. I don't really know how it's going to work. You could probably work it out. So that's kinetic energy. So kinetic energy is tied to how quickly an object moves. So we talked about potential energy is stored energy. So it's how much energy something has when you hold it in the air, whereas kinetic energy is how much energy it has when it moves. We've got two formulas now. Those formulas are mgh down the bottom, and we've got this formula here, mv squared. We've also said that the potential energy depends on how quickly it's falling. Of course, the kinetic energy is going to be how quickly it's falling. The potential is how high it is. Is there a reference energy for kinetic energy? Yes, there is, because there's a point where you say V is 0 when the object is not moving. But just because an object looks like it's not moving, as the example was a car sitting stationary, doesn't mean it's not moving at all. If you took that, it's spinning, the Earth is spinning, so it still has kinetic energy. You just might measure to 0 if you say with reference to the Earth or whatever. So now what we then did this one here. So the next sort of step is to talk about, I wanted to quickly show you guys this concept. Now, I looked online for a picture and I could not find one. I couldn't find a good one. I couldn't find one that I liked. But it's a picture that I've seen a lot in the past. So I thought I would show you guys. If you took that mug, as that mug fell towards the ground, right? You could measure its energy. And you could actually measure its kinetic energy. So its kinetic energy is going to get bigger and bigger and bigger. Okay? So that's its kinetic energy. Its kinetic energy is going to increase until it reaches a point where it hits the ground, and that's going to be its maximum kinetic energy. But its potential energy is stored up in its height. So the very, very start, it has a lot of potential energy. But as time goes on, it's going to lose that potential energy. Let me try that again. It's going to lose that potential energy much better. And so you actually have this idea, and I like this picture because even though this is just another way to think about it, that potential energy goes down and it loses its potential energy. But as the potential energy goes down, the kinetic energy goes up. It gains kinetic energy. And you can sort of almost see that there is a point where it has the same amount of kinetic energy as potential energy, and that's when it's fallen halfway down, because half of its energy is now kinetic energy. There are different graphs for this as well. This is what we refer to as a linear one. The reason this is linear is because it's a drop. But if you were to look at something like a spring, or if you were to look at something like a ball rolling down a hill, these may not necessarily be a linear graph. They will always be, if you look at this, and this is one of the other ideas here, if you were to add these two graphs together, so if you were to say, if this is 1 and this is 9, if this is 3 and this is 7, if this is whatever, if you were to add these two graphs together, you would get a line that looks like this. And this is the total energy. And remember, the thing about total energy is that it's conserved. So even though at the start, all of the energy is potential energy, and at the end, all of the energy is kinetic energy, if you were to add in how much energy is locked up in kinetic energy, how much of it's locked up in potential energy, and add those together, you would always add up to the same value of energy. And that's just another way you can think about this, is that one transfers to the other over time. You could also imagine picking an object out of the air. If you were to stop that object at exactly like 3 seconds in, and you were to measure the amount of energy it has because of its height, the amount of energy it has because of its speed, you could do that. You could figure that out. So that's how we can look at an energy graph. If you guys copied that down, that's great. If you didn't copy that down, it's up to you guys. I'm not going to tell you guys what to copy down or not, but I do think this is an interesting way to think about things. I've tried to use two colors here. Potential energy will usually be drawn in green because I guess it's like stored. I don't know. I'm not going to talk about why I've chosen the colors. It's stupid. Waste of time. So now what I'm going to talk about is I'm going to talk about one more type, and this is the last idea. So there are, as I said, I promised you guys 4 equations. And so we're going to talk about a different way to store energy. Okay, a different type of potential energy. Ultimately, there's only really one form of kinetic energy. It's movement. And there's actually only one equation for kinetic energy, half mv squared. But there are different forms of kinetic energy, so there are different equations. There are different forms of potential energy, so there are different equations. And we could look at the chemical ones. We could go back and look at the heat energy ones that we did before. But we're not going to do that. We're going to talk about one of the other ways that you can store energy with motion, and that's with the spring. This is, by the way, ladies and gents, when I started to get very tired, and so this is where the slides get even lazier. But yeah, we'll see. To compress a spring or to pull an elastic band or anything with a bounce requires a force. You must push or pull the more you must push and pull the more force it releases. The more you push or pull, the more force it releases. Now, what I'm going to try, and I'm really going to try and do my best to really point this out over and over and over again, is this for anything that is with anything with bounce. Now, obviously, we call this Hooke's law or the ideal spring, but anything that has a bounce to it can be thought of as a spring. So if you think about like a mattress, well, mattress has got springs in it, so it's a bad example. But if you think of like, I don't know, a tree, and let's just say you've got this tree, I don't know, you've got this tree, and this tree, it's very windy for me today, so this is going to be a pretty good example. The wind starts to blow on that tree, and that tree actually starts to bend. Okay, that tree, as it bends, this is pretty extreme, but you know, whatever. It's a physics question, so it makes sense. It's going to be extremely drawn. That tree is going to have a force applied to it. It's going to bend. But the second that wind stops blowing on that tree, it's going to fling back up. And that flinging back up action, that bouncing action, that's going to be based off this force. If you push down on your skin and then your skin pops back up, that's you applying a force and you seeing a bounce applied to it. Same with any sort of material. If you look at clothes, if you pull on your clothes and you let go and it bounces back up a little bit, that is an ideal spring. Anything can have a spring-like force, even things that you might think are solid. So you might look at a piece of steel and say, well, that's solid. That's, you know, if I drop that piece of metal on the ground, it's going to be it. But it's still going to compress a little bit. If you drop a wooden fork, if you drop a metal fork on the ground, it will bounce because it will have a little bit of a spring force in it. So, and the amount of force that you need to compress that is going to be, and it's going to be equal to this equation here. So this is what we refer to as Hooke's law. And it says the amount of force that you need to compress an object is equal to negative K times delta X. And K is called the spring constant. So I really should have put this on the slide, but I'm going to add it here anyway. So the larger K is going to be equal, the larger K equals a stiffer spring. So if you've got like a spring from like a car hydraulic, that's going to have a really high K. If you've got something like a piece of, if you've got something like a metal, a knife, that's going to have a really high K because it's not going to bounce very much. It's mostly just going to smack into something. It's going to take a lot to get it to deform. But yeah, it can, if you throw a knife hard enough at a wall, it will bend and then it can rebound. So it can bounce back. So delta X is the spring displacement, or how much it's squished. As for K, the spring constant, it's measured in units. Now, the units that we're going to do, I thought to myself, I could just give you guys the units. But you know what I thought? I thought might be interesting. Why don't I show you how we can work out the units of K? How do you work out the units of K? Well, we know that the units of force are measured in newtons. Okay, we know that the units of displacement are measured in meters. So whatever K has to be, has to convert the meters into newtons. So therefore, you can say, well, therefore K is measured in newtons. And be like, wait, no, it's not, because then that would be newtons times meters would be newton meters. So I have to cancel out this m. How I cancel out this m is I go newton per meter, and that is the units of spring constant. So how did I do that? I said just for future reference, the n on the top is what I want, whereas the m on the bottom is what I must cancel. This is a really good technique, especially if you've got a constant that you're not too sure about. If anyone here is doing chemistry and you're looking at, a lot of you guys are doing chemistry, I've seen. If you guys have seen the PV equals nRT formula, looking at what R is and knowing that you need to get a pressure and a volume term here, you can figure out, well, okay, then R is going to be measured in some kind of weird unit. It's going to be measured in pascals meters cubed over degrees Kelvin times mole, because it needs to cancel out these two and it needs to make these two. So it's a bit of a weird formula. Yeah, it's just a different way you can think about it. Okay, let's look at an example. This is where I got too lazy to make examples up for you guys to solve. So I thought, okay, let's just throw in an example. Let's just do an example. Let's say a spring equal, let's do this, calculate the spring constant for a spring that needs, let's go with, the needs, let's say it's a pretty weak spring, 1.2 newtons of force to compress we'll say that it's only 2 centimeters high, so we'll compress 2 centimeters, so we're squashing it. Now that's not saying that the spring is compressing 2 centimeters. It might be a 3 centimeter spring that's getting compressed down to 1 centimeter, in which case our delta X is equal to 2. And that's what we care about. So therefore we've got the formula F equals Kx. I'm not going to do K delta X because why not? And that negative just means the force is you have to push on it and pull on it is in the opposite direction. But I'm not really going to focus on that too much here. I'm going to drop the negatives, and I do that sometimes. Just ignore negatives and stuff like that if I want to. Try to be a little bit more careful here, but because we're just trying to work out a spring constant, it won't matter too much. So the force F divided by X is going to give you K. In this case, K is going to be the force of 1.2 divided by 2 centimeters. Now we can't use 2 centimeters because that is actually not in meters. We need to convert that to meters. So 2 centimeters equals 0.02 meters. Yes. 1.2 divided by 0.02. 1.2 divided by 0.02 equals 60 newtons per meter. Beautiful. And that's our spring constant for this here. Now, springs are really interesting. Springs are interesting, like just a basic sort of question there. Yeah, and of course, as I keep saying, anything, even a piece of metal that you can bend. If you've ever bent a spoon and then use it to flick someone, then that's using it. Actually, a better example is when you get a ruler. I know that I've seen year 7s do this. They get a wooden ruler and they stretch it a little bit, and then they let go of the end and it flies forward and smacks them. Now, because wood's got a pretty high K, it's going to smack them with a pretty high amount of force. The problem with wood, though, is there's only so much you can deform it. There's only so much you can displace a spring. You can displace a spring by a lot. There's only so much you can deform a wood ruler before it breaks. You might use glass. Well, glass is going to be very difficult to get a spring constant for, because it's only going to deform a very small amount before glass shatters completely. So, yeah, you're not going to be bouncing balls of glass. But saying that, though, I have accidentally dropped glasses onto hard floors before, and they've bounced a little bit and not shattered. I'm like, oh my God, I'm so lucky. By the way, this is just a graph of Hooke's law, 2 pictures here. So you can see here, force by the extension. If you want to extend something by a certain amount, let's just say you've got let's say we've got a spring here and you want to stretch that spring out so it's like this. The more you stretch it, the more force you need to apply. So if I apply this much force, I could stretch it to be this long. And when I let go of it, it's going to fling back down. And when it flings back down, it's going to release that amount of force. But you think about it, if you squash a spring, and this is the last idea here, if you squash a spring and then you let it go, it's going to move. It's going to release a lot of energy. And that's what a spring does, is it stores potential energy. It stores movement energy. You're moving that spring, and then when you let it go, it releases it. Same, of course, if you've got a rope. If you pull on a rope and then you let go and that rope bounces back to its original length, then that's going to be release its energy in the form of motion, or it can do work on something. If you push a spring really, really tight and then you put a block against it, you let go, it will push that block. It will do work against that, work on that block. So that means that when we talk about Hooke's law, we need to also mention energy, and that's where you get this. Hooke's law is a formula that assumes all compression or extension of an elastic object like a spring or a sponge or rubber or rope results in stored energy. That stored energy is calculated using the below formula. EP equals a half K delta X squared. Now, you guys could find a way to convert. You guys could find a way to calculate this. To show how the Hooke's law becomes this law, but I'm not going to do that because I don't really want to. But I'm just going to show you guys this formula. On the right here, I've got a picture of a bungee rope. God damn it! It's pretty good that bungee ropes are elastic. And you might be like, they're obviously not super duper elastic, but they're elastic enough. If they weren't elastic, right? If they weren't elastic, your change of momentum would be, which is equal to force times change in time. Your change of momentum would be very, very, very quick, which would result in a very large amount of force being applied to you. because your change in momentum is, because the change in time is a lot longer, because it's elastic, it takes a long time for the elastic to store your energy and slow you down. Therefore, you don't experience a huge amount of force. If you just jumped off a bridge with just a rope tied around your legs, you would experience that full force on your legs, and that would break your legs more likely. Unlikely to rip you in two, but you never bloody know. It could definitely dislocate your legs. So that's why bungee jump ropes are elastic enough to make sure this delta T term here is a little bit higher. But let's look at now an example. Let's take a rope with, we'll say it's with a spring constant of, you know what, guys, I'm getting a bit tired, so I'm going to use some nice numbers. With 1,000, with a spring constant of 1,000 Newton meters is stretched to be 0.3, which is meters longer than its natural length. How much stored energy is present? Let's calculate this. EP, the amount of potential energy, is equal to half times K and delta X squared, which is going to be a half times 1,000 times 0.3 squared equals 0.5 times 1,000 times 0.3 squared equals 45 is what I got. 45 joules. And so that's how much energy there is. And you might think about that as being, okay, so you've tied this rope down to a heavy block, to an anchor on the ground, and that's how long it's been extended, and then maybe the guideline snaps, and so all of that energy gets released. If all of that energy got released, then how quickly might that rope be moving? And so you might find out, oh, that rope is only weighs very, very little. Maybe it only weighs 30, maybe it only weighs 200 grams or something. So if you divide that if you multiply that by 2 and then divide by 0.2, then that will tell you, and square root that answer, you could figure out how quickly that rope might fling through the air. And that might be a good way as well to look at, if you think about bow and arrow, archery, man, that would have been a really good picture. I should have done an archery here. That's what I should have done here in this one. Oh. If you ever think about archery, right, and believe it or not, a lot of people don't realize when you've got a bow and you've got archery, the majority of the majority of the spring force is not because of the string. The string is actually doesn't have the spring force. The spring force comes from the limbs or the wood. I actually didn't know that when I first. I always thought, oh man, you need to have an elastic string. It's like, no, actually, you don't need to have an elastic string. You need to have an elastic, because that's honestly how they make most toy bows. So they use elastic string. What you need to have is you need to have elastic wood. You need to have wood that can bend. If you don't have wood that can bend, then yeah, you're not going to get much force. And bending wood is really hard, and that's why when you fire an arrow, it fires out really quickly because you are applying a lot of energy to that. And that's also one of the reasons why whenever you go to do archery, you should never let go of a string unless there's an arrow on there, because all of the energy would go straight back into the limbs. It's how you, and I've seen videos of like people who've done that, and then their bow explodes into bits and pieces because like it just can't. It needs to be able to direct its energy into something. And now I'm waffling. I'm sorry.